Okay, the last bit of thermochemistry that we need to cover is essentially endothermic and exothermic reactions, and then we will throw in a little mole ratios with them. There are a big chunk of questions on your final exam that have to do purely with endothermic and exothermic and being able to decipher whether a reaction is endothermic or exothermic based on a variety of factors, like the sign of Q, the sign of H, whether it is hot or cold, what its graph looks like, where it's written in a reaction, and so on. So that's what we're going to go through here. We're going to start with endothermic, and I've written a few things here. I'll speed this up a little bit and get these written in. Endothermic reactions, you need to know that the heat enters. You need to know that it feels cold. You need to know that it has a positive Q and a positive delta H. You need to know that the energy of the products is greater than the energy of the reactants. And you need to know that the heat, or the delta H, is written as a reactant. Okay, it's important that you know all of those. The next thing that I'm doing is drawing a graph here. Again, you need to be able to recognize a graph. Now, for those of you that remember from class, we also talked about this in kinetics and rates of reaction when we were talking about a catalyst also, and activation energy. All of those words, those will come in later when we get to kinetics. Right now, we're just making sure that we understand what an endothermic graph looks like. So here I have drawn an endothermic graph. We always have our reactants and our products. I just used R and P as reactants and products. You can see that the, like we said right here, the energy of our products is greater than the energy of the reactants. That's what we're talking about right here. The energy of the products is greater than the energy of the reactants, because you can think of this as having, let's say it was on a graph here. This is the measure of the energy. Okay, so the energy of products is greater than the energy of the reactants. I sometimes look at this, if you have that curve there, you can imagine what I have in the yellow there is energy going in, and that's why the energy of the products is greater. The products minus the reactants, that's the delta H. You have to for sure know that a positive delta H means that a reaction is endothermic. If you can't seem to remember that, one way you can think of that is that delta H is products minus reactants, which means that in this case it would have to be positive because the products is higher than the reactants. Last thing that you need to be able to know is we're going to address what is on the bottom here. This part right here, that delta H is written as a reactant. One way we can write a reaction is like this. So if I have, let's say, A plus B yields C, and my delta H is positive 50 kilojoules. The fact that it's a positive there tells me that this is endothermic. However, we often don't write our delta H outside of a reaction. We have to put it inside of a reaction. So the other way that I can write this whole thing right here is like so. A plus B plus 50 kilojoules yields C. Okay, when it is, sorry, let me go back real quick there. Sorry about this. Still learning how to use this program. There we go. The sign there is not important, okay, because we never have pluses or minuses within a chemical reaction, only if it's written outside. The fact that it is a reactant is what tells you that this is an endothermic reaction. Okay, so you should take some time to go through this and make sure that you know all of these things about endothermic. Like I said, there's a lot of situations in your final exam where it gives you a reaction and you will know one of these things and you'd have to determine whether that's endothermic or exothermic. Okay, just like we did for endothermic, let's go through an exothermic. I'm going to go through this one a little bit quicker. I'm just going to have it all draw out and then we will talk through it. Okay, so exothermic reactions, the heat exits, it feels hot, has a negative Q, a negative delta H. The energy of the reactants is greater than the energy of the products, and the energy can be written as a product. Again, you're going to see the graph there, and I'll pause here to talk through it. Okay, again, important for you to know these signs are very important, the negatives. Okay, you have to know those. If you can't remember that, you can look at a graph like this, and you can see that it's products minus reactants, and since our products are lower, right down here, than our reactants are, that must be a negative delta H. Another way that you can think of this is if you think of energy being released, it'd be coming out right there. Here's another example of a reaction. One way that we could write a reaction is like that. That's kilojoules there at the end. We have D plus E yields F. Our delta H is negative 10 kilojoules. The fact that it is negative there is what tells me that it's exothermic. However, again, a lot of times we don't write delta H outside of the reaction. We put it in the reaction. And when that is the case, the energy is written as a product. Now, remember I told you that we never have positives. This isn't a math equation, so we never have positives or negatives inside a reaction. The fact that it's written as a product is what tells us that it is exothermic. Now, I apparently used the same example from last time. This should be, of course, the 10 kilojoules. So we'll fix that, 10 kilojoules, because that's what it was up above there. What you, again, need to recognize is that when it is written as a product, that is exothermic. Another thing that I want to point out is that sometimes you won't see it as a value. Sometimes you'll just see it as something that looks like this. Okay, obviously if it has a value, we throw that in, but if not, you will sometimes just see it as heat. So those are endothermic and exothermic. Those are great things to quiz each other on, and make sure you definitely review those before the final exam. Last topic is thermochem and mole ratios. I like to stay away from the term stoichiometry because it tends to scare a few of you, so I'm just going to leave it as mole ratios. Okay, we're not going to go into the whole stoich with it. You're not going to be able, or you're not going to have to do that on your final exam. So we're going to use this equation right here. 2A plus B yields 3C plus 10 kilojoules. Now what I'm going to do is put up a few things here, and we're going to see if I can, well, let's go through the whole first one here together. What I did is I just took the coefficients that each of the substances has to start, and I just said that 2 moles of A equals 10 kilojoules. 1 mole of B would produce 10 kilojoules of heat. 3 moles of C would produce 10 kilojoules of heat. Okay, again, we're just looking at the mole ratios. That means that if I have, this time instead of having 1 mole of B, if I have 2 moles of B, how much heat would I produce? Since it's a 1 to 10 ratio, and I'm multiplying B by 2, then I must multiply 10 by 2, and I get 20 kilojoules. Okay, next one, if I had 9 moles of C, that would be 3 times as many, which would mean 3 times as much heat, so it would be 30 kilojoules. If I only had 1 mole of A, that's half the amount of A that I have in my equation, which would mean half the amount of heat. Okay, so those are easy. When it's just twice as much or half as much. Okay, sometimes we might have to do a little bit of the mole problems though. Like let's say I have 1.8 moles of C. Remember, I can always use that train tracks method. And I would say if I have 1.8 moles of C, there are 3 moles of C for every 10 kilojoules. Moles of C will cancel, and I will get 6 kilojoules. Another example problem, 5.4 moles of A. Let's say I started with that. Why don't you pause this real quick and solve for that answer. There are 2 moles of A for every 10 kilojoules. Moles of A would cancel, so I get 27 kilojoules. The other way that you can see these problems is by actually starting with heat. You do the problems the exact same way. This time you're just going to have your ratio inverted so that kilojoules is on the bottom, so that kilojoules will cancel. So for this one, there are 10 kilojoules, and it depends on what I'm solving for. Let's say in this case, I am solving for B. So then I would have 10 kilojoules for every 1 mole of B. Kilojoules will cancel, and I end up with 1.65 moles of B. Alright, those problems shouldn't be too hard. Again, I know that I've said this multiple times, but it is important for you to go through all of that endothermic and exothermic stuff and know it for your final exam.